Okay, assalamu alaikum. Good afternoon, all. So let us start our class. I will go to the presentation. So I hope my voice is audible. Okay, so in today's class, we are going to see some theoretical relations which is related to the jet propulsion. So we call it as a jet propulsion theory. I hope I am audible and I can continue with the same pace. Yes. So in the jet propulsion theory, so we'll use the word thrust. Thrust is nothing but with respect to your jet or rocket engines. We call it as it is nothing but the propulsive force, a momentum which is used to propel the jet engines. So how do we get this thrust? What we'll do, we use a high velocity jet in some way. uh, that only we are going to see. We will let us take in some way we are going to get a high velocity jet when it is coming out from the a nozzle or over the propeller. By we know that by Newton's third law, we'll get an opposite force. So that force only we call it as a thrust force. So that is being used to propel the any jet engines. There are two types of thrust we can understand. One is called propeller thrust. Another one we have jet thrust. There are two types of thrust on there. The obtaining thrust in two systems is slightly different, but the basic the principle is going to be same. If you say in this right hand side, we have written F equal to m dot into change in velocity. So this is we all know that this is from our Newton's second law of motion. F equal to m into a. M into a is mass into acceleration. That we'll be using it for our solids. Like in our engineering mechanics, we have studied Newton's second law of motion. F equal to m into in dynamics, we might have studied. Here we don't have any solids; it is fluid. So when it is a fluid, mass will become mass flow rate. When mass will become mass flow rate, so we'll have only velocity, correct? No need of acceleration because mass flow rate kg per second, velocity meters per second. Okay, so that we'll be getting in Newton unit, correct? And if I'm just multiplying with this velocity, I will not get I can able to get just the force only. See, there has to be a change in velocity. There has to be a change in velocity, then only there will be change in force that I can call it as a momentum. Momentum is nothing but some impact, some force. So when there is a change in momentum, when there is a change in velocity, then only we'll have a change in momentum. That's why we'll put change in velocity. So there has to be a significant change in velocity should be done. Otherwise, we have to provide the possibilities. Then only we'll get a corresponding change in momentum. That momentum only we call it as a this thrust force. So how do we get this in the case of a propeller thrust? We can have a rotating propeller we might have seen, correct? Generally, it will be rotating at very high RPM. The speed is not a moderate speed like in our motor and all. Okay. So 4,000, 5,000, 6,000. Okay. RPM is very high. The reason is we need to get a very high change in velocity. Correspondingly, we get a momentum. If you closely look into this, this is the velocity of the fluid. This velocity of the fluid is the speed at which the jet is moving or flight is moving, the same speed air will be coming. That's why it is called velocity of the jet or flight speed. When it comes here, so when it just crosses this propeller, uh, naturally a boundary will be formed that we call it as a flow boundary. Inside this boundary, the fluid will be in rapid motion. Here, the velocity will be relatively less outside this boundary because it is closer to the propeller here. And further, when the air is when the air is passing through this, you see, just it is just crossing this propeller. Propeller is rotating at very high uh, the rotational speed. So it will be just that rotational speed will be transferred to the fluid just crossing this propeller blade. What will happen immediately? The velocity gain will be there because this energy is transferred to this fluid here, correct? And it just crosses this, C1 will become C2 when it comes here, correct? C2, and if you closely observe this flow boundary will just form it as just like a nozzle like profile, so that there will be a further rise in velocity. Rise in velocity is not that much significant. The rise in velocity is only due to the propeller rotation. When it just come here, when it just comes, the fluid is just crossing the propeller blades, so its energy will be transferred to this. So that huge change in velocity, and further when it moves here, okay, so when the fluid is just crossing this, it just slipping over the blades. That's why it's called as a that flow stream. We call it as a slip stream. And there will be a further rise in velocity when it makes a nozzle like a passage because the flow will take in that way. So when I'm measuring a section here, so then I'll be getting a velocity, then I can call it as a velocity that is enhanced velocity, jet velocity. Otherwise, we call it as a slipstream velocity. We'll use the word CJ, and this is the flight speed. And so this difference in velocity multiplies the mass flow rate. So you'll get a momentum. You just see that these three terms are just directly proportional to the this F here, correct? So that means when there is a more change in velocity, more momentum, correct? And similarly, more mass flow rate of air. If I'm sending more amount of air, okay, so that I'll be getting higher amount of F. So it depends on the amount of air also. So amount of air flowing over it, more the uh, mass flow of air, more the momentum, because it's directly proportional. So it depends on the mass flow rate of air. Mass flow rate of air is less, so momentum will be, again it will be less. It is proportional to that the term which are on the right hand side. Okay, so in this way we obtain uh, the propeller thrust. Is a very important relation, and we'll use in another performance parameter with respect to these two velocities, namely flight speed and jet speed. We call it as a flight speed to jet speed ratio. So we'll use in some of the later derivations. We'll be using it. Okay. Okay. Next, jet thrust. A jet thrust is we obtain thrust when the gas is expanded in the nozzle. This is applicable for any gas turbine engines. If you see the gas turbine engines flow diagram, normally we'll have a diffuser. Sometimes compressor may also be there. After that, we'll have combustion chamber and then turbine. The turbine exhaust will be coming to this nozzle. After expanding in the turbine, the hot gas will be allowed to expand through this nozzle here. So during expansion, we all know that we already have studied in our thermal engineering steam nozzles. So just a similar thing that we can understand here. For understanding this, the flow parameters, we'll form a boundary here. There will be appreciable change in flow properties across this boundary. So that means this will be taken for analysis. That's why we call it as a control surface. When we do the analysis, so we'll consider the exactly the flow properties at the boundary here and also inside. So that's why we have this boundary. We call it as a controlled surface, and we have control volume also. In the case of a jet thrust, there are two types of thrust will be produced. One we call it as a momentum thrust, another one is called as the pressure thrust. Momentum thrust is just similar to the in our previous case what we discussed. When there is a change in velocity of the uh, fluid, here expansion of gas will be there in the nozzle when it comes out. So it will be the velocity, we call it as the exit velocity of the nozzle. Otherwise, exit velocity of the gas at the nozzle, not at nozzle. We use we use the word like this, and this is nothing but your flight speed. So this difference in velocity, in addition to this mass flow rate, so will give us the momentum thrust. Sometimes we'll use this relation if significant amount of mass flow rate of the fail is considered. That is mass of the fail is significant, then we'll use this relation. Means in our yesterday's class we have seen when it comes to the exhaust gas, it is nothing but air and fuel mixture, correct? After combustion product only. This one is nothing but just an air. That's why mass flow rate of air is multiplied with that flight speed. If mass flow rate of the fuel is negligible uh, compared to the air flow rate, negligible in the sense we have to compare with this. So then in that case we'll use this, just similar to our previous relation. There is another thrust called pressure thrust will also involving here. So what is this pressure thrust here? Uh, when you see it here, the nozzle is expanding here. Gas is expanding in the nozzle. So there will be a velocity gain corresponding drop in pressure will be there, right? So we'll use the word complete expansion and incomplete expansion in the nozzle. Complete expansion in the nozzle is when uh, when the gas is expanding, the outlet pressure, that is the pressure at the exit of the nozzle, will be equal to the ambient condition. If it is so, then we can call it as a complete expansion. See, the pressure will be generally higher inside this gas, correct? Inside the your nozzle, gas pressure will be generally higher because the temperature is higher there. So to what extent I am lowering the pressure, corresponding gain in velocity will be there. So that means if I am, what is the minimum pressure here? Only atmospheric pressure. Right? Beyond that, we cannot be able to reduce it because the minimum pressure is the surrounding pressure there. So that means this is nothing but your gas pressure, and the gas pressure is reducing, correspondingly velocity is increasing there. So when I keep on reducing the gas pressure here, So if nozzle is very effective, so if it is an effective design, so that I can the expansion will be taking place, so that my nozzle gas exit gas pressure at the nozzle exit will be equal to the ambient pressure. In that case, there won't be any, this PE will be equal to PA. There won't be any pressure thrust will be there. If it is incomplete expansion, so this will be involving here. Means your gas pressure, nozzle exit, and ambient pressure. The pressure is nothing but you see that this is the pressure multiply with this area only, will be getting a force. Correct, Amma? Pressure Newton per meter square and area is meter square. So meter square gets cancelled and I'll be getting the force Newton. That's why we need to multiply with the pressure into area here to getting the unit of force here. So that means what we can understand here, this pressure thrust you see it here, this this P is not correct. This P is on the right and towards right. This PA is on the towards left. So ambient pressure is acting opposite to the direction of your exit pressure. This direction is towards right. Okay, this is wrong here. So that means if there is a complete expansion, this will not be there. Incomplete expansion, this will be there. That means if it is incomplete expansion, so this is offering some resistance for the your- on the total thrust. So if there is a complete expansion, only we'll be getting the momentum only with respect to the change in velocity here. So if the incomplete expansion is that, then we'll be getting a slightly reduced momentum here. So in that way, we can understand the jet thrust when a gas turbine engine is producing with the help of a nozzle here. So sometimes we'll make this C equal to Cj. In that case, we'll use F equal to m dot A into Cj minus Cu here. So based on the data, sometimes we'll take C equal to Cj and we'll use just m dot equal to Cj minus U into m dot A if mass flow rate of the fuel is negligible. So in that way, we'll use the relation for jet thrust as well as the propeller thrust. Next, we have some performance parameters. In terms of efficiencies, we are going to obtain the relations. There are three types of efficiencies: propulsive efficiencies, thermal efficiency, and the overall efficiency. So this is our gas turbine engines. So we are going to give heat input. What is the heat input? Calorific value of the fuel, that is QF, and multiplied the mass flow rate. So that is nothing but the total heat energy given. And this is going to produce some kinetic energy of mv square. This is nothing but our engine power or power output of the engine of mv square corresponding to the fuel power given. So this we'll call it as a power output of the engine or engine power. Okay. So when my thrust is multiplied with the velocity, what will be the unit? Thrust is N and U is meters per second. It is Newton meters per second. It is joules per second watts. So this thrust multiplied with the velocity, we call it as a thrust power, a rate of energy per unit time. So here we use this word thrust power in association with this your thrust and also the jet speed. I mean flight speed U. Okay. So based on this relationship, we are going to obtain this relation for this propulsive, thermal, and overall efficiencies. Propulsive efficiency in the sense, so in the numerator, how much amount of propulsive power is produced? What is the power output of the engine? So actually, this power output of the engine is the actual power, correct? With respect to the heat input given. So corresponding to that, how much thrust is produced? Actually, with respect to the fuel, you got this power output. So how much amount of propulsive power corresponding to that has been produced? So for that, we use this efficiency, call it as a propulsive efficiency. So the propulsive power or thrust power, we have F into U. F is m dot into Cj minus U. U will be that. And the power output of the engine will put off m dot Cj square minus U square here. We'll simplify this. So how do you simplify? It is very simple here. What we can here for simplifying this is a square minus b square. A plus b minus a plus b minus a minus b. கரெக்டாமா a square minus b square உடைய ஃபார்முலா யூஸ் பண்ணிருக்காங்க. A plus b into a minus b. அப்ப என்ன ஆயிடும்? You have when have Cj minus u, you have Cj minus u on the numerator and also denominator. Both gets cancelled. These two will go up and mass flow rate get cancelled. So only thing is we have Cj plus u. So our relation is simplified relation 2u by Cj plus u. Further, it can be simplified with respect to that the one parameter we got. It is flight to jet speed ratio. So that relation we have used it here. Okay. So by using that, we can obtain this relation propulsive efficiency equal to 2 sigma by 1 plus sigma. Sigma is nothing but our flight to jet speed ratio. In either way, we can use this relation propulsive efficiency. Correct. Next, another relation thermal efficiency. Thermal efficiency we know very well. This is nothing but output and input comparison. Output is you see that we have a power output here. Input is nothing but how much amount of heat energy we are given. That is nothing but your input. So we know the what is the power input we are given as a heat energy. That is going to be your calorific value of the fuel. QF is nothing but calorific value of the fuel multiplied with the mass flow rate of the fuel. Amount of heat energy supplied. Power output of the engine. So we have it here of m dot into Cj square minus v square. That will give us the thermal efficiency. And overall efficiency. Overall efficiency is what is the basic input? We have some heat energy that we are given. What is the final output? We have got some power output, but that has to be converted into a propulsive force. That is propulsive force. We call it as a propulsive power. Propulsion, that is thrust. Correct? Thrust to produce. We have some heat input. Ultimately, I need some thrust. Correct? So that has to be compared here. I'm giving some heat input through fuel. Finally, I need some thrust. And the thrust I'll put in the numerator in proper units. So how? Because this is the rate of energy transfer. So that here the thrust has to be multiplied with the velocity. So that I'll be calling it as a propulsive power here. Correct. So in that way, the overall efficiency is nothing but the propulsive power and the heat energy available in the fuel. So the propulsive power F into U. F is m dot into Cj minus U into U by m dot F into Qf here. We can also obtain this propulsive overall efficiency by multiplying this propulsive efficiency and thermal efficiency. You see it here. When I am writing the propulsive efficiency relation, this is m dot into Cj minus U into U by of m dot Cj square minus U square. Similarly, thermal efficiency. This also you know that output by input here. We can cancel these two of m dot Cj square minus U square both in the numerator and denominator. So it gives the relation just for overall efficiency. So we can understand overall efficiency can also be calculated if you know the propulsive efficiency and the thermal efficiency. Okay, these three performance parameters we call it as an efficiency we'll be using. And like in our internal combustion engines, so we have some other performance parameter. Specific fuel consumption. TSFC means thrust specific fuel consumption. That is nothing but mass flow rate of the fuel per unit thrust produced. Mass flow rate. There, what we use in our BSFC, brake specific fuel consumption. Mass flow rate of the fuel per unit brake power produced. Per unit brake power produced. So in the same way, we use this mass flow rate of the fuel per unit thrust produced. And we use another performance parameter, specific thrust and impulse. The specific thrust is nothing but this is inverse of this. Thrust produced per unit mass flow rate of the fuel. If mass flow rate of the field is significant, then we'll use m dot a plus m dot m. Sometimes mass flow rate of the field will be negligible. In that case, we'll use just m dot a. Similarly, we have another parameter, impulse. This is nothing but thrust produced per unit weight flow rate of the field. W dot. That is, we have to multiply with the acceleration due to gravity here. So that we'll call it as a specific thrust, as well as next one is specific impulse. So these are all mm, the basic performance parameters. We'll be using it while analyzing these jet engines. So based on this, we are going to solve some problems. Okay, Vama. So before that, we need to see one more theory part. We'll complete this. We have because of jet engines, we for enhancing the thrust produced, we use various methods. So one such method, we call it as a thrust augmentation. General thrust augmentation is a general word. We'll use various methods for this thrust augmentation. So one such method is what we'll do. We'll use a process called reheating, so that we can increase the thermal efficiency, and we'll get some enhanced thrust. Now we know what is the meaning of thrust. So let us see how we we obtain some enhanced thrust. Considering our jet engines, we have inlet diffuser. After that, we have compressor and combustion chamber turbine. We use this reheater, and finally we'll have nozzle. We know the thermodynamic process involved in this jet engines. The diffuser is used for raising the pressure of the incoming air. So the air pressure will be increased, and further pressure is increased here. So when I'm using the diffuser, the uh, the power required to increase the pressure here will be reduced in the compressor, so that I can enhance the economy of this entire gas turbine plant. That's why we use this compressor here, a diffuser, increase the pressure. Further, we'll increase the compressor, so pressure and temperature is increased. Then it goes to the combustion chamber. Supply the fuel. So we have a hot air. Combustion is taking place. So we get a hot gas combustion product is coming out from this combustion chamber. It enters to the turbine. Expansion is taking place. The power out produced in the turbine is used to drive the compressor here. And actually, this will be a small compressor only, because we could not spend much energy on this, because most of the energy has to be spent at the nozzle, and the expansion has to be the heat energy, maximum part of the heat energy to be spent on the nozzle. Okay, so that loss which has taken place in the turbine, that is due to the expansion, some heat loss will be there, correct? The expansion of heat energy only we obtain this shaft power output. So we'll supply it to this reheater here. Reheat in the sense, this is an ideal, we call it as a reheater. In actual case, again some combustion will be taking place, so that will raise the again its temperature and pressure here, so that the heat energy gain will be there. So higher the heat energy in of the gas when it is expanded in the nozzle, so enthalpy drop, correct? So more the enthalpy drop is converted into your what is that, gain in kinetic energy. What is the equation? Nozzle நம்ம படிச்சிருக்கோம். V2 equal to root of 2 into H1 minus H2. Enthalpy drop. எவ்வளவு தூரம் enthalpy drop இருக்கோ, corresponding that we'll be getting the velocity gain. So more the heat energy we need. So the same is represented in our temperature entropy diagram. You can see it here. So I to 1 is nothing but a pressure rise and also the temperature rise in the diffuser, further rise in pressure and temperature in the case of a compressor here. So when it goes to a combustion chamber, so there is a because of the combustion, rise in pressure, a rise in temperature as well as pressure. And when it goes to 3, 4, so there is expansion is taking place. So there will be enthalpy drop, corresponding temperature drop will also be there. 4 to 5, so we try to increase the unit's temperature again with the help of a reheating process. Not to that previous level, be below that level. So that again there is a gain in the gain in heat energy here. You see it, instead of just sending at this stage, we are raising the temperature to this level and we are expanding in the nozzle. So that definitely we get enhanced thrust at the nozzle. That's why we call it as a thrust augmentation. So in this way, the thermal efficiency is nothing but thermal efficiency. We are increasing the thermal efficiency of this gas turbine engine, and also we are getting an enhanced thrust. Correct. Okay. So this is all about the theoretical part related to our jet propulsion part. So we'll see one problem on this. Whatever the relations we have seen, based on this, we'll see one problem. Okay, so let me read this. Will the doubt come on? You have any doubt in this part? This relation only we are going to use it now. Huh? Okay. A turbojet engine takes in 50 kg per second of air and propels an aircraft with a uniform flight speed of 800 km per hour. Isentropic enthalpy change for the nozzle, that is the enthalpy drop, is 188 kilojoules per kg and its velocity coefficient is 0.96. The fuel air ratio is 1.2 percentage. Combustion efficiency is 95 percentage. Calorific value of the fuel is 44 into 10 power 3 kilojoules per kg. We need to calculate the thermal efficiency, propulsive overall efficiency, as well as mass flow rate of the fuel. So these problems are very easy only. So the relations we are going directly substitute, we are going to get it. Direct substitution, easy. The thing is we need to clearly understand the data given here. So writing the given data, mass flow rate of the air is 50 kg per second, and they given it as the flight speed. Flight speed, we use the notation u. It is around 800 km per hour. It's a normal. If you see it here, if you normal passenger aircraft speed எவ்வளோ இருக்கும் நார்மலாக இட் இஸ் அரௌண்ட் 1900 1200 அந்த ஸ்பீடில் தான் இருக்கும், அதான் நார்மல் ஸ்பீடு, அந்த ரேஞ்சு தான். ஸோ இட் இஸ் 880 km per hour and we can convert into meters per second. We need only in meters per second, correct? So kilometer into 1000 we'll get meters. To convert in seconds, it is in hour, so dividing by 3600, so we'll get 244.4 meters per second. And they given it as the enthalpy change, so I'll put it as the change in enthalpy as 188 into 10 power 3 joules per kg. And they given another what is called the coefficient of velocity. Okay, this I'll come to this later. And mass flow rate of the fuel and mass flow rate of the air, that ratio they given, that is 1.2 percentage. So we'll never use percentage in calculation, we'll put it in fraction, 0.012. So since it is fuel air ratio, I'll write mass flow rate of the fuel by mass flow rate of air. The combustion efficiency is 0.95. Calorific value of the fuel is given 44 into 10 power 3 kilojoules, 10 power 6 joules per kg. So first we'll obtain the because for getting a thrust F and all, we need gas velocity and flight speed. The difference we need. So first we'll get the nozzle exit velocity. This nozzle exit velocity, we have to remember our steam nozzles. Correct, amma? Steam nozzles discuss pannom illaya. Root of 2 into H2 minus H1 enthalpy drop. They directly given the enthalpy drop here, so that I am going to put it. And this is nothing but like in our what is that, in our flow measuring devices, you see that Our venturi meter, orifice meter, what we'll do, you will use coefficient of discharge. What is the meaning of that coefficient of discharge? Is always maximum one. It is always actual case it will be less than 1. 0.8, 0.9, 0.7 like that we'll use. So what is that actually? Coefficient of discharge is nothing but it is the comparison of actual and theoretical discharge. That means some theoretical discharge values that actual discharge will be always less than with respect to that particular uh, flow measuring devices, either it is the orifice meter or venturi meter. If actual discharge is equal to the theoretical discharge, what you have calculated. The purpose of orifice meter, venturi meter, and all to give a maximum discharge. Correct? Maximum discharge means if theoretical discharge is going to be the maximum discharge. If it is equal to the actual discharge, it is 1. So no loss. No loss in the discharge. So that will not be there in the real case. Okay. So we'll use less than 1 that will multiply with this. Similar to that coefficient of velocity, some loss will be there, isn't it? So that loss, some velocity loss is there that they are given in terms of this coefficient of velocity there. So we are going to multiply with this 0.96. Correct. That is less than 1. So something is with respect to the loss here that we do not know in what way that loss has occurred. So this is going to be reduction in the jet velocity. So that will just multiply with this CV in this entire term 0.96. So that we'll get our exit velocity as 588.6 meters per second. And you see it here, we have seen here the expansion. There are two possibilities. One is complete expansion and incomplete expansion. If it is a complete expansion, what we'll do, our nozzle exit velocity will be equal to the our jet velocity. That is P equal to PA in that case. So we'll assume here it is isentropic expansion. Isentropic expansion means no loss where a gas pressure is expanded so that it is equal to the ambient condition. So in that way, we'll assume it because even it is given that isentropic expansion, no loss. So in that case, we'll take C equal to Cj here. So this is going to be the jet velocity. And with this ratio, we can able to get our mass flow rate of the fuel. Right? This ratio has been given mass flow rate of the fuel, mass flow rate of air into this 0.012. We'll get mass flow rate of the fuel as 0.6 kg per second. We just see that mass flow rate of the air is 50 and it is 0.6. You see the comparison, the difference between the quantity of air and the quantity of fuel. That's why in most of the cases we neglect the mass flow rate of the fuel comparing with the air quantity. Okay. Okay. So here we are going to consider it because when you know the mass flow rate of the fuel, we can consider. And we know that our thrust relation F equal to m dot A into Cj minus U. The mass flow rate is significant or if it is given, what we can use this relation. It is m dot A plus m dot F into Cj minus m dot A into U. You can see it here, this relation. This relation we can use it. Otherwise, you can see it here, this one. Okay. So this m dot will get m dot A plus m dot F 50.6 into our Cj is 588.6 minus m dot A is 50 into our flight speed 244.4. So F equal to thrust produced 17.56 10 power 3 Newton. Next, thermal efficiency. Thermal efficiency is output by input through the fuel. So output is our the kinetic energy of m dot our v square or c square is in of m dot into cj square minus u square. And if you see in our the relation here, use m dot f into q of is nothing but our calorific value. Here they are given it as combustion efficiency. If no such word has come, what will do? There is no loss during the combustion. So something is some loss has occurred. So what we'll do? We'll just multiply this combustion efficiency here. That means we can write in another way also. Combustion efficiency equal to actual heat supplied by ideal heat supply. Actual heat supplied is combustion. This is nothing but ideal heat supplied into 0.9. In that way also we can write it. Otherwise, you can simply multiply with the combustion efficiency. No such combustion efficiency has been given. We will consider as it is 100%. No loss. We'll just multiply with 1 and that we can understand. We will substitute mass flow rate of the fuel as well as the calorific value of the fuel, 44 into 10 power 6 into 0.95. F we have calculated, and also you also we know 244.4. So overall efficiency, okay. So we are here, correct? Okay. So thermal efficiency m dot f into qf into 0.95 of into m dot is your m dot a plus m dot f 50.6 and cj square. We know that jet velocity as well as flight speed also we know. So zero point 0.6 into calorific value into your 0.95 your combustion efficiency. So we'll get our thermal efficiency as 28.9%. And propulsive efficiency, we have a simple relation for the propulsive efficiency. What is that? It is 2u by Cj plus u. This relation we can use it easily. 2u by Cj plus u. U is 244.4. Cj also we know. U also we know. So that we'll get our propulsive efficiency as 58.6%. Coming to the overall efficiency is propulsive power by power input through the fuel. Propulsive efficiency is F into U. I mean, your propulsive power is F into U, correct? So F is thrust produced. We calculate 17.56 into 10 power 3. Flight speed 244.4. We know mass flow rate of the fuel, calorific value into combustion efficiency. So we get our overall efficiency as 17%. It will be relatively less because thermal efficiency is very low always. It will be around 30-35% only. That's why the overall efficiency is also less because whenever you use the heat energy, whenever we try to utilize the heat energy and we convert into power output, always the efficiency will be less. It will affect the overall efficiency also. There are a lot of heat loss. Heat energy is the low grade energy. So I hope, my dear friends, you understood this problem. It's a very basic problems to understand when we try to understand the performance of jet engines. We have some more problems. We'll see it. We are going to solve it. Problems like this. Okay, I think we can close this for today's class. Now, what I will do, I'll just show you for taking a screenshot. You can take it, please. In thrust augmentation. Okay, next to this problem. Okay, so I will wait for some time. Please see that. Have any doubt? This, need any clarification? Okay, ma'am. I think if you have no other doubts, so I can close the presentation. So I'll take attendance. His answer attendance 49, 49 Shakila.
Yes, sir. Present, sir. 49.
Yes. And 50
Yes,
Shakil.
sir. 50%, sir.
Okay.
57%, sir.
7 Faizuddin. Yes.
Present, sir.
Yes. 60 Qasim Imtiaz.
Present, sir.
Okay. And 75 Kiraj.
Present.
Okay. 94
Yes, sir. Present, sir. 94.
Sunil Sanjay. Okay. 2016 Icon. Streetcon 2016, 2017 Suraj.
70% sir.
Yes. 2019 Arshad.
Sir, 2016 present, sir.
Okay. Arshad. Okay, ma'am. Thank you. Meet now next.